been a while since I've recorded one of these. So this video is looking at potential and electric field for continuous charge distributions. The electric field stuff we've already learned how to calculate using Gauss's law and the integration of Coulomb's law. And we're going to look at the connection between that and the way we do that for potential as well. Specifically, we're going to look at V and delta V in the vicinity of distributed charge. It's important because sometimes we can find the potential as an absolute relative to zero, but sometimes we can't. And that will be near the end of this as we look at infinite charge distributions. So far, we have these two relationships. We have the fact that kind of the Coulomb's law-esque relationship of potential is the sum of the KQ over R's of point charges. And if you only have a few of those, that's reasonable. What we're going to do now is we're going to say, well, the continuous version of that would be the integral of K dQ over R over some space to get the total potential from that charge distribution. Or we will use the fact that we determined that the change in potential is negative of the integral of E dot dr. That was going back to our work in energy relationships and realizing that the electric force and the electric field and the electric potential energy and the electric potential change, which is like work, are related to each other in the same way. So we're going to look at examples using all the different methods. This is all in Unit 10. You're in your packet, page 22. You can follow along with these derivations if you like. Probably makes the most sense. So example one, potential and electric field at the end of a line segment. Now we've already done this for the electric potential, so now we want to do this for the electric field. We're going to do this for the electric potential. The big difference here is that potential, of course, is a scalar, so we don't have to worry about the vector nature of it. We have a little bit of dq, which is showing up here in red. We're going to integrate K lambda dr because we can't integrate with respect to charge. We're going to integrate with respect to R or position. In this case, we could really just be doing this in the x direction, but we'll call that R. R is the distance from point P to the charge. So we're going to integrate from R1 to R2 or R initial to R final. And this is a 1 over R relationship. So the integral of that is the natural log. And then we get RF over RI, plug in those values. We end up with a particular potential at that point in space due to all of that charge. Right? The basic idea is that each little bit of charge has less and less of an effect as you get further and further away. So we can also do the electric field, which we've done before. Right? The vector contributions are all in the same direction, and we can get that value as well. Right? And again, this is something that we did last time. Not last time. This we did back in, I guess, Unit 8. It's been a little while now, but it's that same principle. We've also done the electric field for a ring of charge. And so we're going to do this now for the electric potential. What is potential as a function of position x is really what we're looking for. Well, we know that V is the integral of K dq over R. The dq is a little bit there. The R's are all the same, right, for a given x, which is nice. And R is the square root of R squared plus X squared, because that's a little right triangle form there using Pythagorean. So everything's a constant here for a given X, right? So we don't actually need to integrate this, which is kind of fun. So we set up an integral. We didn't actually have to do the integration because R is a constant for any given value of X. And that's really all we're looking for. And you could then plot that. For the electric field, remember we had to do this bit where we had to use only the X components of the electric field. So we had to do a little bit of substitution. And again, this is a little bit of a review. The electric field here is to the left and is equal to that value there. And really, again, depending on the only thing there that is not constant potentially is the X. So now we can do some interesting things. If we place a proton at point P, right, and we talk about how fast will it be going after it's repelled, right? This is a positive charge. It'll be pushed to the left. Well, the potential at point P is KQ over that square root of R squared plus X squared, which we can calculate, 7,200 volts. The conservation of energy relationship should get us there. We start with no kinetic energy because we're placing it there and releasing it from rest. We have some electric potential. And when it's infinitely far away, it will have all kinetic energy. So that's our criteria for maximum velocity. So what we can do is replace electric potential energy with Q times the electric potential. We already have the potential. And 1/2 mv squared for our kinetic energy. Solve for V final. And we put everything in. I'll move my picture out of the way. We get 1.2 times 10 to the 6th meters per second. So pretty fast. We can look at a sphere of uniform charge density, same basic idea here. We've already looked at these because we said, oh, well, we can just assume that shell theorems apply. No integration is actually needed. We know how to do these, KQ over R, as long as you're outside of it. So that's the easy part. Once we get inside, we'll have to do a little bit of work. On the surface, right at the surface, still no integration needed. We're just right on the outside, radially outward for electric field and the max potential or a high potential there. Again, the important thing to notice is this is not a conductor. If it were, all the charge would be on the surface. So now that we're going inside, we have to find the electric field using Gauss's law, which is something we've done before. You draw a Gaussian surface, the surface integral of E dot dA, Q enclosed over epsilon naught. And the electric field is Q, R over a bunch of constants. In other words, it's 0 at the center and it gets bigger as you go outward, right? KQ over R cubed is our constant, set of constants times R. Inside the sphere, it increases linearly with R. Now, once we have that, we're going to use this to deal with the fact that we don't exactly know what's happening at the center, right? So we're going to go back to our graphical relationship. We know that when you're at a distance R from the center, outside the sphere, you start with KQ over R squared, and the electric field goes like 1 over R squared. Inside the sphere, we have a linear relationship. But if we want to find the potential within the sphere, we have to be a little bit more careful. We don't know, right, how to, well, we could, I'll say this, we could add up by integrating KQ over R, all the bits of charge around the sphere, but it's not spherically symmetric if you're at some point C, a distance from some distance from the center to the outside. So what we're going to do is we're going to say, well, we know the potential at B, and we know that we could find the change in potential between 2 points using another method. And if we could add a potential we know plus a change of potential from that point to the next point, we should be able to solve this. So we're going to start with that KQ over R that we already calculated for point B when you're on the outside. And then we're going to use this integral form, the integral from basically capital R into some point little r of E dot dr, with the negative sign out there, to figure out how much the potential changes. We're basically dealing with the fact that the electric field is pointing outward here and dr is going inward. And so we can get the positive by flipping those, right? The only difference between integrating from capital R to little r and little r to capital R is the sign. So now it's plus. We evaluate this at R and capital R and little r. The capital R is, of course, a constant. We can simplify this down, and we end up with something that may or may not be obvious, right? This doesn't, when I look at this, this doesn't jump out at me and go, oh, I know what that means. But essentially what this is saying is that we have R squared over R, which is a value that has to be less than 1, right? And the closer R squared is to capital R, right, the closer that gets to 1, right? That fraction. And when R squared over R is 1, then that's 3 minus 1, so it's 2, and the 2 cancels out, and you just get KQ over R. And so V max is going to happen when R is 0, because little r is 0, because you're not subtracting anything from this potential. And so what does that look like? Well, KQ over R happens at R, and it's a 1 over R relationship when you're outside of the sphere. But inside, it increases and reaches a maximum where it sort of flattens out at 0. And that's 3 KQ over 2R. So 3 halves of what is found at the surface. And the big thing to pay attention to here, right, is that our relationship that says V, or change in V, is equal to negative integral of E dot dr, we can turn that around and say the electric field should be negative dV dr. And if you look at the electric field, it starts at 0, which is the slope of the graph of potential at the beginning. And it gets more and more positive. Notice it gets more and more negatively sloped on V, so that fits. Then as we leave it, right, we've got multiple compound curves here, but one of them is a 1 over r on the V side. And if you take the derivative of that, you would get, that's to the -1. So you would get to the -2, which is a 1 over r squared relationship on the electric field side. So that's finite distributions of charge. But what about infinite distributions? We already know that in some ways these are simpler because there's uniform fields or very predictable fields. But we're going to need to use that similar technique we just used about moving from one point to another to find potential differences here as well. So infinite plane of charge. This is, I think, on page 25, if my numbers are correct in your packet. What is the electric field for this? Well, we've already done that calculation. We draw a Gaussian surface. It takes sigma, some surface charge density, times the area that's cut out by that cylinder. The 2EA, sigma A over epsilon naught, the A's cancel out. We end up with a nice constant electric field, sigma over 2 epsilon naught, right? Again, that was something we did back in Unit 8. But now that we have that, we can start to talk about what is the potential difference from one point to another. It's important to remember that we can't talk about a place where there's zero potential. That's because there's an infinite amount of charge here. You can't get infinitely far away, right? That doesn't make any sense. So all we can do is say, well, what's the potential between points A and B, right? If the field is uniform, you can never go to a place where the field stops affecting the charged particles. You can never get to a place where there's zero electric potential energy for a single charged particle. It's always going to be pushing against the field to move it around or with it. So what we're going to do is just find a potential difference between 2 points in space. So here we've got A and B, which are about 45 centimeters apart. The number isn't terribly important, but it allows us to do the calculation, right? Change in potential, or the potential difference, the voltage between these 2 points, is the negative integral from A to B of E dot dr. That's our formula. We, in this case, have a nice situation. We don't actually need to compute the integral because electric field is constant. And the integral of dr from A to B is just the distance from A to B. We're calling d here. And we get actually a fairly simple answer, 150,000 volts. So this is probably the easiest one, right? The voltage rises as you go from A to B because you're going against the electric field, and it decreases as you go the other way. So last example here, an infinite conducting cylinder of charge. So this is basically a chunk of metal, a wire, if you will. And we want to figure out what's the electric field when you're outside of it. We've already done this one. It's this spherically symmetric. Answer, lambda L over epsilon naught is our charge enclosed. We end up with a 1 over r relationship, right? It's a radially symmetric, goes like 1 over r. What is the potential difference between r and little r, where r is greater than big R, when you're outside, basically? When you're going to integrate from A to B, right, from the surface on out, and when you're outside, you have an electric field that you know, so 1 over r relationship. If you integrate that, you get a natural log. And so as you're going further away, the change in potential is negative because it's getting a weaker electric field. If this is a positively charged cylinder, it would be the opposite if it were a negatively charged cylinder. So that is the technique. You could also do this with a charged, uniformly charged insulator, a cylinder of that. You'd have to do some more of the integration stuff, but those are the examples that are really the most important. We can use these integration techniques to find either the potential in some cases or just the potential difference between 2 points near some continuous distribution of charge.